Okay, so this is a review session going over the practice final exam 2020 fall. Okay, first question says that consider the two-form field on R3 given by beta is that, and part A says compute and simplify dB. Okay, so we can take the derivative directly. For example, we get dB is, I look at what variables I have in my expression. So I have an x and I have a z. So that means I should take the partials with respect to x first. So that means I have 1 dx and add on the wedges. And then the partial with respect to z. That gives me 1 again, dz, and then add on the wedges. Plus, now I look at my second expression and I have a z in there. So I'm going to take the partial with respect to z, which gives me 1 dz. And then I add on the other wedges, dx, wedge, dy. So now that we have this, let's see if we can simplify anything. So we see that we have an x and an x here, and we know that when wedges repeat, that goes to 0. What else do we have? We see z and a z here. So that's a double thing, cancels out to 0. And all we're left with is dz, wedge, dx, wedge, dy. And if you wanted to, you can rewrite it as dx, wedge, dy, wedge, dz. Okay. Part B says to integrate beta over the parameterized surface. So we can remember so we're trying to integrate beta. Another way to write this formula is we're going to do the double integral of beta with our parameterization plugged in, multiplied by our Jacobian matrix or the derivative, ds dt. So we can think about it in that way. And what can we do? What exactly is this saying? It's like we have this two form. Or sorry, it's a 3 form, I guess now. And it is, no, actually beta is a 2 form. Okay, beta is a 2 form because we have a wedge product. So it's a 2 form, and what is this? It's like eating in 2 vectors. DG is going to be a matrix with 2 columns. So we have a 2 form eating 2 vectors. And so there's lots of ways you can approach this problem. You can either make your parameterization and then plug in your parameterization here. And then the wedge products represent area projected to that specific plane. Or we can do it the vector way, where we do a big determinant. So let me try it the vector way, so we see a different way of doing things. What is our function going to be? So first, let me write my function. What should my vector field be? Well, the vector field is always written as the first component dy for some 2 form written like this, f2 dz wedge dx plus f3 dx wedge dy. The associated form for the vector field is f1, f2, f3. So in this case, what are our f1, f2, f3? In this case, our f1 is whatever's in front of the dy dz. There's no dy dz anywhere, so it's 0. Do we have a dz wedge dx? Yes, we do. That's the x plus z term. X plus z. And do we have a dx wedge dy term? Yes, that's the z. So that's our vector field. Now they gave us the parameterization already in the question. Our parameterization is s plus t, st, and then t minus s, where s goes from 0 to 1, t goes from 0 to 1. So when I do the integral of beta, it's the same as doing the double integral of, I make this big matrix where I write my components of my vector field from 0, x plus z, z. And I need to write what is my derivative. So I should have calculated that first. The derivative with respect to s gives me 1, t, negative 1. Partial with respect to t's give me 1, s, and 1. So I write those in my other columns. Okay, and I should be evaluating this at my parameterization. So I'll just write this for now. ds dt. What are our bounds? They gave them to us. S goes from 0 to 1, t goes from 0 to 1. So s goes from 0 to 1, t goes from 0 to 1. Okay. What are we missing? We have this double integral. But I don't want like x's and z's in here. So that's why I want to plug in my parameterization into my expressions. So here I get 0. What is x plus z? X plus z is s plus t minus s. So that means I have 2t because x plus z is s plus t minus s. S is cancelled, so I get 2t. And what is z? Z is t minus s, according to my parameterization. And I have this, the remaining, these things. Okay, so now I can do minor expansion to find the determinant of this matrix. So I'm going to minor expand using the top row. I get 0 times something, which I know is 0, minus 1 times the remaining matrix, plus 1 times the remaining matrix. Okay, and with some simplification, so I have 0 to 1 of this is 2t minus st plus s squared plus negative 2t minus t squared plus st. And this is like a bunch of algebra. I will simplify it to 4t plus 2st minus s squared minus t squared yes dt. Okay, and integral I will get 11 over 6. Okay, if anyone wants to actually see the work for this, just put a thumbs up or I will move on. Okay, any other questions on problem 1 then? Okay, let's do a problem 2.
Could you scroll back up just for 2 seconds to the part A?
Mhm.
Okay.
Yep.
Thank you.
Okay, so this part B, I use like this method, but again, there's lots of ways that you could have done this question. And you should still get the same answer. Okay. Question 2. Consider the parameterized curve. Part A, compute the velocity vector. So to compute the velocity vector, I take the derivatives component-wise. Right, so I look at my first term, which is t cosine t. The derivative with respect to t is, I use product rule. So first term times the derivative of the second term, plus second term times derivative of first term. Derivative of negative 4t is negative 4. We have t cosine t plus sine t, and then 3. Okay, part B, set up but do not solve an integral to compute the arc length of this curve. So what is the formula for arc length? We know that any smiley face equals integral d smiley face. So if I wanted to find the length, the arc length, that's going to be the integral of the arc length element. What is the arc length element? Well, that's the derivative. The length of the derivative dt is the arc length element. So I have an integral from a to b of, well, what is my derivative? I already found it in part A. So I just have to find the length of it. The length of any vector is square root of each of the components squared. So I have my first component squared, plus my second thing squared, plus my third thing squared, plus 3 squared. Okay, and this requires some simplification. So here we have like t squared sine squared t minus. So when you're squaring things, don't forget you have to do the foiling. This doesn't just become this squared plus this squared. So you have a minus t cosine t sine t coming out plus minus t cosine t sine t plus cosine squared t plus 16. So this is just, you can write it all out, and it's a bunch of simplification. You'll need to use the trig identity, cosine squared plus sine squared equals 1. And so eventually you'll get down to t squared plus 26 dt. But what are our bounds going to be for my integral? Well, they give me my bounds, so that's nice of them. T goes from negative pi to pi. So I have t going from negative pi to pi. And that's how you find the arc length. And they said don't solve it, but that's enough. Okay, part C. This curve intersects the origin at t equals 0. What angle does the curve make with the positive x4 axis? Okay, so in order to find the angle between two vectors, I know that formula, right? That's the cosine equals dot product over the length formula. So let me write our formula. Cosine theta goes u dot v over a length of u length of v. But in order to use this formula, we need two vectors. So what do I have right now? Right now, I have some parametrized curve in R4. So this is some random curve. And it says that it intersects the origin when t equals 0. So at t equals 0, I intersect the origin. And we have a curve, but I can't just use a curve in my equation, in my formula. I need an actual vector. So what can I do? What if I took the derivative of the curve at t equals 0? Then that would give me a vector that's tangent to my curve at t equals 0. So what is the green curve? Well, I found my derivative already. That was part A. So all I have to do is plug in 0 for t into my part A formula. So when I plug in 0, I get 0 plus 1. That's 1. I have negative 4, 0, and then 3. So that's my first vector. I'll call it u. And the question is asking, what angle does it make with the positive x4 axis? What is the x4 axis? The x4 axis is all zeros everywhere, except you have a 1 in the fourth component. And I'll call that b. Right, just like how, as an aside, what do we call the z-axis? We always call it 0, 0, 1, or like the cave axis, something. Okay, so we have our two vectors, v and u. Now I can follow my formula. Cosine of theta equals 1, negative 4, 0, 3, dot with 0, 0, 0, 1, all over the length. Length is square root of each component squared. And then the length of this is 1 squared. So we have that cosine is 3 over square root 26. In other words, theta is going to be arc cosine of 3 over square root 26. Okay, and I have a question in the chat. Why is it 1 and not the x4 point at which the vector intersects the x4 axis? So because it's saying like what angle does the curve make with the positive x4 axis, and if you are considering like where it intersects, like at which vector it intersects x4, like you don't have enough information for that, I guess. And even if you say like the origin, then this question doesn't make sense. Like you would be multiplying by 0, 0, 0, 0. So we always say like what represents the x4 axis in general. It's always 0, 0, 0, 1. Just like when we have like a normal vector in the upward pointing direction, we call that the z-axis or 0, 0, 1. So it's just like an arbitrary vector. Okay, any other questions on problem 2? Okay, question 3. Consider the vector field on R3 given by this vector field. Part A says compute the divergence of F. Okay, we know how to do the divergence, right? The divergence of F is written as this triangle del dot F. What is the divergence? It's the partial with respect to X of my first component. It's very long, so I'll just highlight what I mean. Plus the partial with respect to Y of the J component. Plus the partial with respect to Z of our last component, which is 0. So what do I get? The partial with respect to X of this, you have X squared sine Z. So I have X squared sine Z. And in here, partial with respect to X is Y squared. Plus, what's the partial with respect to Y of this thing? Well, I can just look at this inner thing. What's the partials with respect to Y? I get 3x squared plus 3y squared. And that sine Z still stays because it's like a constant. And then plus 0. So I have that it's, how can I rewrite this? I have x squared sine Z plus y squared sine Z plus 3x squared sine Z plus 3y squared sine Z. I can combine like terms. Here I have the x squared sine Z, so that's 4x squared sine Z. Here I have 4y squared sine Z. In other words, I have 4x squared plus y squared sine Z. Okay. Then part B, compute the flux across the entire boundary of the closed cylinder. So the keywords I'm seeing are flux. Flux is a signal I should be using Gauss. Let's make sure, what do I need in order to use Gauss? I need a closed 3D object that's like enclosing some volume. So let's see what else they say across some boundary of a closed cylinder, including the end caps. So because it's including the end caps, that means that I do have a closed 3D cylinder that's enclosing some volume. So I can use Gauss. So what does Gauss's theorem say? Gauss's theorem says that if I want to do the integral of f dot n d sigma, by Gauss, it's going to be over some boundary. It's going to be the triple integral of my entire domain of divergence dV. And that's nice because I already found in part A, what is the divergence? The divergence was, I found up here, 4 times x squared plus y squared sine Z dV. So I have this triple integral. I have a cylinder though. So I could keep doing this integral out in Cartesian coordinates, but why would I want to do that when I could do cylindrical coordinates? Because I have a cylinder. So let's convert to cylindrical. If you wanted to keep it in Cartesian coordinates, you would have like a bunch of square roots and have to deal with a lot of squares and square roots and stuff. So let's convert to cylindrical. When I convert to cylindrical, that's why I wrote part A in this way, because in cylindrical coordinates, what is x squared plus y squared? That's r squared. So my integrand is 4r squared sine Z. When I convert to cylindrical, what is dV? dV becomes r dz dr d theta. And then what about my bounds? Well, I have a cylinder. So what should my z bounds be? I like draw a line in the increasing z direction. What surface does it enter first? They tell me that it enters the z equals 0 surface, and then it exits the z equals pi surface. Those are my z bounds, 0 to pi. Then I imagine collapsing the z-axis. When I collapse the z-axis, what do I get? According to the problem, I have a circle of radius 2. X squared plus y squared less than or equal to 4. So that means my r goes from 0 to whatever the radius is, that's 2. And then theta, we have our entire cylinder, no limitations. So theta is still 0 to 2 pi. Okay, and so if I did this integration, I will do one part. So let's take the integral with respect to z. What do we get? We get 4r cubed. So this is an r squared r. And integral of sine z is negative cosine z. From z equals 0 to pi, we r d theta. So that means I have this integral. Cosine of pi, so I have negative 4 cubed. Cosine of pi is negative 1. Cosine of 0 is 1. We r d theta. Okay, and I could keep continuing this, and I get 64 pi. So question in chat, we got part A wrong due to a mistake, and we use the results of part A. Do I get some partial credits if I do B correct with the wrong answer? You should ideally, yeah, you should be able to get partial credit as long as you're showing like you've plugged in, you show that you know you're where you're supposed to plug things in. And if you like actually try to work out the integral, then yes, you should get partial credit. Okay. Part C, carefully explain why the flux of F across each of the end caps of the cylinder is 0. So we have a cylinder, a closed cylinder, and part B, we got an answer of 64 pi. Why is the flux across the end caps 0? Well, let's consider what is Gauss's theorem again. So using the forms version, right? Gauss's theorem can also be written in this way. You have the integral of dV. Okay, and what exactly is Vf? That's our two form, the two form associated with my vector field. So my two form would be this whole highlighted yellow thing. So a third, I'll just write highlighted thing, dy wedge dz, plus the green highlighted thing, dz wedge dx, and there's no dx dy term. And then Gauss's theorem would say we take the derivative of that. The derivative of it would be some 3 form, dx wedge dy wedge dz, with maybe some other stuff, but in general, it's a 3 form. What is a 3 form doing? A 3 form measures projected volume, right? Just like how a 2 form measures projected area to the YZ plane or whatever variable plane. Triple wedge product measures projected volume. But what is our surface in this case? They're asking us about the end caps. The end caps are flat. They're the z equals 0 plane and the z equals pi plane. So our surfaces are flat end caps, which end caps. And if they're flat, well, there's no area, or sorry, no volume, right? Because it's flat. There's no like 3D thing. It's just a 2D surface with no volume. So that's why the flux across the end cap would give you 0, because there's no volume. So you should get 0. Or integral of equals 0.
Could we also claim that it's 0 because the K component of the flux is 0, therefore there is no flux going vertically like in the Z direction?
Yes, so that would be that would be essentially using Stokes' theorem instead. So Stokes' theorem says like you do the curl dot n d sigma, and n is the z because our normals are pointing in the upward direction, so it's the z-axis 0, 0, 1. And then as you pointed out, the curl component, the last thing would be 0 essentially. And so you see that if you did this dotted with 0, 0, 1, you get 0. So yes, same argument.
Sorry, for part B, how did you get positive 64 pi? Because we evaluated cosine z from z equals 0 to pi, right? But isn't cosine is 0, 1?
Cosine of pi is -1, and cosine of 0 is 1.
Wait, why do we evaluate from top to bottom? Isn't it bottom first?
like, oh, like, so I guess whenever, like, if you had v from 1 to 2 dz, let me call it dx. Like, how do we integrate that?
Oh, sorry, I completely just forgot how to integrate. Never mind.
Yeah, so you always take the top one minus the bottom. Okay. Other questions on problem 3? Okay, problem 4. Consider the 4x4 matrix. Use row reduction and back substitution to solve the linear system. Okay, and they say this is of the form, right, ax equals to b. So 2 ways to solve an ax equals b problem. You can either say x is a inverse b, but we have a 4x4 matrix. We don't want to find the inverse of that. That's so much work. Like, you would have to do row reduction again. So instead we can do make an augmented matrix and then row reduce and then back substitute, which is what they recommended. Back substitute. Okay, so how should we do this? We have ax equals b written here. I make a big augmented matrix. So my A is this matrix. 0, 1, 1, 2, 5, -3, 11, -5. And then I could do a little dotted line and I write my B vector, 4, 4, -7, 8. And the goal is to row reduce. So let's see what we can do. What I always want to start off with is that I have either like a 1 or a -1 in the top left corner. If I have that, I'm good. I can move on. Next step I want to do, well, I don't want this -3 here because my goal is that I want eventually an upper triangular matrix. So let me get rid of that 3. How am I going to get rid of it? I'm going to say R3 is row 3. What if I add 3 of row 1? So I'm doing a combination. Then my first row stays the same. Second row stays the same. And the last row is still the same. But I have -3 plus 3 times 1 is 0. 5 minus 6 is -1. 1 minus 0 is 1. And then -3 plus 15 is 4. And then over here I have 5. Okay, so I'm almost there, almost at my upper triangular state, but I have this -1 here. I don't want that. So what can I do? I can either do another combination thing if I wanted to, but notice that the second row and the third row, if I just switch their positions, then I get 1 step closer to my upper triangular form. So why don't we do that? I'm going to switch row 3 and row 2. That means my first row is still the same. Last row still the same, but I'm going to switch the 2 middle rows. -1, 1, 4, 5, and then 0, 0, 1, -3, 4. Okay, almost there, almost at my upper triangular. I still have this 2. I don't want that 2. So let's do another reduction. I want row 4 to be row 4. How can I get rid of it? I usually look to the row above it and I see, oh, I can subtract 2 row 3. So -2 row 3. Then I get my whole first 3 rows are the same. So let me just copy paste. The last row is going to be 0, 0. 2 minus 2 is 0. -5 plus 6 is 1. And 8 minus 8 is 0. Okay, at this point, you could keep row reducing if you wanted to until you get to a diagonal matrix. And then you could directly read off x4 is whatever is here, x3 is here, x2 is here, x1 is here. Or I can stop at this point and just do row back substitution. Meaning I look at my last row, that's x4. x4 is 0, because I have x4 equals 0. My next row is x3 minus 3x4 equals 4. I already know what x4 is. I just solved for it. It's 0. So that means that my x3 is 4. Second row, tells me negative x2 plus x3 plus 4x4 equals 5. I just solved for x3, that was 4. And then x4 was 0. So that means negative x2 is 1 or x2 is negative 1. And finally, my first row gives me x1 minus 2x2 plus 5x4 equals 4. So x1 minus 2 times negative 1 plus 0 equals 4. In other words, x1 plus 2 equals 4, so x1 equals 2. So my solution is x1, x2, x3, x4 equals 2, negative 1, 4, 0. Okay, so any questions on part A? Okay, part B says compute the determinant of the matrix A. Right, so let's just focus on my squares that are happening. Because I've essentially already done the row reduction that I need. Okay, so this is my matrix A. This is my reduced matrix R. What is the determinant of R, my reduced matrix? The determinant of R is, well, now that it's in an upper triangular form, I can just multiply the terms on the diagonal, which are 1, negative 1, 1, and 1. So I get negative 1. But I need to get back to A. So what is the formula? Determinant of A equals determinant of R divided by whatever changes I made. So what changes did I make? I did a combination that multiplies my determinant by 1. I did a switching that multiplies my determinant by negative 1. And then I did another combination, which is no change, meaning multiplied by 1. So I have, what is determinant of R? It was negative 1. What are the changes I made? I have a 1 here, a negative 1, and then another 1. So my final answer of the determinant of A is 1. That's part B. Okay. Any questions on problem 4? Okay, question 5. So consider the function. Part A, find and classify all 3 critical points of A. Okay, so I have my function. How now in single variable calculus, what would we do? We take the derivative, set it equal to 0 to get the critical points, and then do the first and second derivative test to classify it. But right now we're in multivariable calculus. There's multiple inputs. There's multiple inputs. So we can't just do a simple derivative, but we do have a kind of analog, and that's the derivative matrix or the Jacobian. What is the derivative? df? Well, that's going to be, I only have one output. I have one output and 2 inputs, which means what should the size of my matrix be? It should be a 1/2 matrix. So I have one output, so 1 row, and 2 inputs, 2 columns. So partial with respect to x is 8 minus 4x minus y squared. And the partial with respect to y is 2y minus 2xy. To get the critical points, the analog is that I want to set it equal to 0 everywhere. So what happens when I set this equals to 0? So I set this equal to 0. And we want to set this equal to 0 as well. Okay, let's look at this one first, because, just because. So let's factor this out. 2y, I can factor out a 2y and it becomes 1 minus x. Again, there's lots of approaches. If you decide to use this one first, it should still work out. I use this one first, so I'll do that version. This gives me y equals 0. This gives me x equals 1. Okay, so if x equals 1, what does that mean for my derivative? If I plug it in here, plug in x equals to 1, I get 8 minus 4 minus y squared equals 0. In other words, 4 minus y squared equals 0. So I have negative y squared minus 4 equals 0. So negative y plus 2, y minus 2 equals 0. So y equals negative 2 and 2. So my possible critical points so far are 1, negative 2, and 1, positive 2. Okay, what else? What about y equals 0? We have to deal with that. If y equals 0, let's plug it into this partial. So plug in y equals 0. That means I get 8 minus 4x minus 0 equals 0. So negative 4x equals negative 8. In other words, x equals 2. So I have another critical point, 2, 0. Okay, so I found all 3 of my critical points. Now we have to classify it. How do we classify critical points? We have the second derivative test. Second derivative test. And that's using the Hessian. So that was all those rules, like looking at the sign of the Hessian, and then possibly you have to look at the sign of the determinant and the trace. So let's find the Hessian. Hessian is the second derivative matrix. What is that defined as? It's defined as partial of x 2 times. Here we have partial with respect to x, then y. Here is, oh, wait, this should be x. Here we have y, then x. And then here we have y twice. Okay, so that means I look at this. Partial with respect to x gives me negative 4. Partial of this with respect to y gives me negative 2y. And let me just double check that my off diagonals are the same. If I take the partial of this with respect to x, I also get negative 2y. That's good. And then this partial with respect to y is 2 minus 2x. 2 minus 2x. That's my Hessian matrix. What does the second derivative test say? I plug in my critical points into the Hessian. So one of my critical points is 1, negative 2. That was this first point. So what happens? I get negative 4. Negative 2 times negative 2 is 4. Here I get 4 again, and then 0. The determinant of this matrix is 0 minus 16, which is negative. What does a negative second derivative matrix say? It's a saddle point. So at 1, negative 2, we have a saddle. Let's look at another critical point. What about our second critical point? 1, 2. Well, I plug those into my Hessian and I get negative 4, negative 4, negative 4, 0. And the determinant again is negative 16. So I get negative sign, so it's a saddle point again. Lastly, my last critical point is 2, 0. So Hessian matrix evaluated at 2, 0. That gives me negative 4, 0, 0. 2 minus 4 is negative 2. The determinant of this is 8. That's positive. So that means I know right now that it's a local extrema. But is it a max or a min? Well, I have to look at the trace. What's the trace? I add the terms on the main diagonal. Main diagonal meaning top left to bottom right. So I do negative 4 plus negative 2. That's negative 6. And we know that a negative trace means it's a local max. Okay, so I've found my critical points and I've classified them. Any questions so far? Okay, part B. If f is constrained to the curve where this equals 9, then what set of equations will be used to solve the constrained optimization problem? So whenever I see constrained optimization, immediately think Lagrange. Like that's what you want to think. What does Lagrange say? Lagrange says, given some function f and some constraint g, we can set up the equations as gradient of f equals lambda gradient g. What is f? F is the function they give me, the 8x plus y squared minus 2x squared minus xy squared. What is g? G is my constraint. So they're saying f is constrained to this curve. So my g is going to be this exact equation, 2x squared minus xy plus 2y squared, and I can subtract over the 9 as well. So this is my constraint. And I'll write my function as well. My function that they gave us in the original question was this equation. So what is the gradient? Well, I have two inputs, so my gradient should be like a column with two terms. Partial with respect to x is first. That gives me 8 minus 4x minus y squared. Partial with respect to y is 2y minus 2xy. And I set it equal to lambda times what is the gradient of g? Well, the partial with respect to x is 4x minus y. Partial with respect to y is negative x plus 4y. Okay, so I have two equations so far from this formula. I have this equals lambda 4x minus y. I have 2y minus 2xy equals lambda negative x plus 4y. But don't forget, this was from Lagrange. But don't forget, we always also add in our constraint equation. This is from constraints. So they said, just set it up. We don't have to solve. This is the setup. We have two equations from Lagrange plus our constraint equations. Any questions on problem 5?
Wait, can you go over the third one again? I got confused there.
Yeah, so the third, so I always have my equations from Lagrange, and then the last one is the formula from my constraint equation. So that was this equation. So I can, yeah. So I just wrote it with the minus 9 equals 0, but you can also write equals 9 if you want.
All right, thank you.
Okay. All right, question 6. For some value of C, the following is a probability density on the unit ball. Compute the value of C. So whenever you see probability density, think that, what does it mean? Like, what's our maximum probability? It's always like 100% or 1. So the idea with a probability density function, PDF, is that the integral of the density should always equal 1, should always give you 1. And they're telling us that the probability density function is exactly this. So to do part A, we want to set the integral of our probability density function, which they're saying is c x squared plus y squared plus z squared to 5 halves. We want to set it equal to 1 and solve. Let's look at our shape. What is our shape? We have a unit ball. Let me draw our sphere. Lengths of 1. X, Y, Z. Okay, so again, I can solve this using Cartesian coordinates, but that would require lots of square roots and everything, because the equation of a sphere itself is x squared plus y squared plus z squared equals radius squared 1. But I don't like square roots, so if we have a sphere, let's convert to spherical. So what happens when I convert to spherical? Let me write this c on the outside. C is a constant, right? So I'm going to write it on the outside. And I'm going to focus on my integral. So I always have a c. I have a triple integral. What is x squared plus y squared plus z squared in spherical coordinates? That's equal to rho squared. So I have rho squared all to the 5/2 power. What is dv in spherical coordinates? That's rho squared sine phi d rho d phi d theta. What are my bounds going to be? Well, I have an entire sphere. So my bound for rho is going to be 0 because it starts at the center and I'm still in my region. What is the radius of my sphere? It's 1. So I go to 1. What is the greatest range of phi I have? It's 0 to pi because I have my entire sphere. So 0 to pi. And then theta, I have no limitations again. I have my entire sphere. So it's 0 to 2 pi. Okay, so I can type C times, I'll just do some first step. So what is this? Actually, let me just keep rewriting it. Okay, here I have rho squared all to the 5/2 power. When I do exponents like these, what it does is it multiplies the exponents. So these 2's will cancel out, and I'm left with rho to the 5th times rho squared sine phi. 0 d phi d theta. What is rho to the 5th times rho squared? When I'm multiplying things, I can add the exponent. So this becomes rho to the 7th. So I have this integral. When I take the integral with respect to phi, what do I get? Well, the sine phi, with respect to rho, sine phi is acting like a constant. Integral of rho to the 7th is rho to the 8th over 8. 0 to 1. D phi d theta. So I have this thing. Okay, when I plug in 1 here, I get 1/8. So I have 1/8 sine phi. When I plug in 0, this becomes 0. So minus 0. D phi d theta. And I can keep doing this integration. I will get c pi over 2. And remember that that was all set equal to 1. These were all like 1 equal, 1 equal, 1 equal. So when I solve for c, I get c equals 2 over pi. If anyone wants to see this, just put a thumbs up or in the chat. Okay, part B. Compute the probability that a point in the unit ball chosen at random with this density lies within 1/3 of the boundary sphere. In other words, they give you this greater than 2/3. So what does that mean? So I have my sphere. Let me move it down here so I can draw more. This is part B. And they're telling me that I only want to consider the region where x squared plus y squared plus z squared is greater than or equal to 2/3. So let me first mark my 2/3 square root 2/3 radius. And I get a ball or a sphere with radius square root 2/3. I only want the region of my sphere that's greater than this radius, which means I only want this highlighted region. Okay, and so I want to find the probability that I'm in this region. So what can I say? Probability that your density is within, or you have like a point within 1/3 of boundary, equals to, well, it should be the triple integral of your density function, dv. Right? What is our density function? Our density function is, let's keep things in spherical, right? So we look at spherical coordinates. We had rho to the 7th c. What is c? It's 2 over pi. So I can write 2 over pi, and my density was 2 over pi rho to the 7th. So this was my density function. with my C plugged in, because I just found what C is in part A. And when I convert to spherical coordinates, right, I have a row, sorry, I also had that sine phi, d rho, d phi, d theta. Okay, and what are my boundaries going to be, my bounds? Well, rho should go from, now we don't start at 0, because if we start at 0, that means that where I am in my region, I should have my region when I'm starting at 0, but I don't. This is like an entire hole. If I draw a line radially outwards, where do I start? I start at this circle, which is square root 2 over pi, or square root 2 over 3. So my rho starts at this radius, and it ends at the 1 radius still. Phi again, my phi is not affected by the fact that there's a hole in here, because I still have my entire like region. What is the greatest angle I can make with the positive z-axis? It's still 0 to pi. And then when I collapse my sphere, I still get an entire circle, and I still have all the regions. Like imagine I collapse to the xy plane. I still have my entire circle, so it's still 0 to 2 pi. Okay. And we can do that, and I got 1 minus 2/3 the 4th power.
Wait, can you explain why P is, like, why is it just in 2/3 thing?
Yeah, because so when we had our entire sphere, rho started at 0. That's because how do you get the rho bounds? You always draw a line radially outwards. And so when we had our whole sphere, it could start at 0, because at 0, I'm in my region. And then I went all the way out to 1. But right now, if I started at 0, that's not part of my region. My region is only the highlighted part. So I have to start at whatever this shape is. And that is the sphere with radius square root 2 over 3. So that's why I start with my rho at 2 over 3. I keep going radially outwards, and the maximum is still the sphere of radius 1. So my upper bound is 1. Any other questions on 6? Okay, problem 7. Consider the following functions. And note that each takes the origin to origin. Okay, so in other words, we know, yeah, okay. Part A, compute the derivatives. Okay, so if I take the derivative of f, what do I get? Well, I have partial with respect to x, gives me a negative sign, but the negatives cancel, so 3 sine 3x. And partial with respect to y is 2e2y. Partial with respect to x here is negative 5. Partial with respect to y is 2 cosine 2y. Then I look at dg. What is that derivative? Well, I have 2 variables, 2 outputs, so make sure you're always thinking about the dimensions as well. Like make sure the dimensions of your matrices are the correct sizes. Partial with respect to u is 2 minus v squared. With respect to y is 3, or v is 3 minus 2ub. Partial with respect to u is 3, and then 4 minus 3v squared. Okay. Part B, compute the derivative of this composition evaluated at the origin. So here you want to say, what are you using first? Whenever I see derivative of some composition, think chain rule. Chain rule says that the derivative of f of g at some point A is equal to df evaluated at our like innermost function at the point. So this has to be g of A, not just A. And then times dg at A. Okay, what is our A right now? They're asking for evaluated at the origin. That means my A is 0, 0, the origin. How do I know it's 0, 0 and not like 0, 0, 0, 3 zeros? Well, A should be the input of like G, and G has 2 inputs. So I know my origin should be just having 2 zeros. Okay, what is G of A? G of A is G of 0, 0. And I could plug it in here to confirm, but they also tell us each takes the origin to the origin. So I definitely know that G of 0, 0 should also be 0, 0.
For DG in like part A, how did you get 4 minus 3v squared?
Oh, it should be plus.
Okay.
So note that for this type of question, like you would want to make sure that you've written this equation and you show that you know G of 0, 0 equals 0, 0. Because otherwise, like say you didn't know and you just wrote, like you didn't write the equation, like you didn't write the equation and you just said, oh, df at 0, 0 times dg at 0, 0. Like we're not sure that, like you haven't shown that you know this should actually be G of A. It was just by coincidence that like you got 0, 0. Like it's just by coincidence that G of 0, 0 happened to be 0, 0. So make sure you don't just assume that. You want to make sure you're showing this should be G of A. Okay, so what does that mean for us? E of f of G at 0, 0 equals, what is df at 0, 0? So I'm plugging in 0 everywhere here. And I get 0, 2, -5, cosine of 0 is 1, so this is 2, times dg at 0, 0 gives me 2, 3, and then 3, and then 4. So I get 6, -4, 8, -7. Okay, part C, if the outputs of G at the origin are changing at rates -3, -4, then at what rates are the 2 inputs changing? So now they've given me the outputs and I want to find the inputs. So what does that sound like? That sounds like like you have a derivative times the rate of change of outputs. So some derivative times the rate of change of outputs. What are the outputs? The outputs are changing at -3, -4. -3, -4. So the derivative times some rate of change of inputs equals the rate of change of outputs. Right, this is like saying rate of change. Let me write the general formula. Rate of change of outputs equals some derivative of whatever you're doing times rate of change of inputs. So they're telling me, why do I use dg? Well, they tell me that it's outputs of G only. So that's why I'm using derivative of G, not derivative of the composition. Okay, and what is the derivative of G at 0, 0? That's this matrix, the 2, 3, 3, 4. UV equals -3, -4. So here again, we have an AX equal B question. Because it's a smaller 2 by 2 matrix, let me try solving it using the inverse way. So inverse way says X equals A inverse B. In other words, X equals, what's the inverse of this matrix? The formula for that is 1 over the determinant. The determinant is 8 minus 9. I switch the main diagonal terms and I negate the off diagonal terms. Okay, and then times B. B is -3, -4. So I have 1 over -1. Here I have -12 plus 12 is 0. And then 9 minus 8 is 1. So I get 0, -1.
You could have also made your like augmented matrix, right?
Yes, you can also do augmented matrix. This is method 1, method 2, augmented matrix. Now, sometimes, so it didn't happen in this case. In this case, our DG is a square matrix, which is nice, and it's only 2 by 2. So I could use this inverse way. But say your derivative matrix was a 3 by 2 matrix or something. Let me say a 2 by 3. 2x3 matrix. So something here. So I had like that times UV W equals -3, -4. Say I had something like that. And we know that there's two ways, the A inverse B way or the augmented way. And you say, oh, this is a 2x3 matrix. The inverse doesn't exist. So I say no solution. I would say not exactly. So this method will only work in the case where your matrix is square, but that doesn't necessarily mean you don't have an answer. So if it turned out that this isn't square, I would recommend using the augmented matrix way because you might still get an answer. So this might not be no solution. You might actually have a UVW equals something. Okay. Any questions on problem 7? Okay. And yeah, that's the end of the exam.